Hello everyone. I think previous lecture was extended for a few minutes. So we'll wait couple of minutes because still students are joining and then we'll start. Till that, am I audible? And can you see the shared screen? Yes, anyone can respond. Can you see the screen? Hello. Hello. Okay, no problem. So let us start. So yesterday we started about multi-threading and Mandar Mehta, mute yourself. So yesterday we started with concepts of multi-threading, and this was an important thing I just mentioned, the concurrency versus parallelism. Meaning of both is like multiple tasks can be executed and they can make progress. Only thing is with concurrency what happens is because there is a single core, there is a switching between the tasks. So single processor will execute any one of the tasks at a time. Whereas whenever we have a multiple cores, that is multiple processors, then all the tasks can be executed simultaneously. That is what the parallelism is. Then I mentioned about this Amdhal's law. This is important even for gate-like examinations. So this law talks about the computation speed up because of additional number of cores added, that is additional number of processors added into the operating system. So for example, if there is a single core and that takes some time to complete the task for operating system. Now if I add one more core there, then theoretically, let me tell you, theoretically, the speed up should be double, but that won't happen, right? That is one thing. And second thing is the speed up mainly depends on the serial processing. Serial processing component is there. Let me tell you, for example, suppose I want to take two numbers and I want to perform some sort of operations like addition, multiplication, division. Okay. So now suppose what I'll do is for addition, separate thread is there. For multiplication, separate thread is there. For division, separate thread is there. So all three operations can be performed parallelly, simultaneously. Okay. But then the thing is, all these three threads cannot be started until we get the input. So if we assume like one thread is there, or my one program is there in which I am reading two numbers, maybe like in C language, something like scanf. So thread 1 for addition, thread 2 for subtraction, sorry, I guess I mentioned multiplication, and thread number 3 for division. Or even subtraction also you can consider. So 4 threads 4 operations. These 4 operations cannot be started until and unless we take the input from the user. So whatever the code is there till taking the input from the user, you can consider that as the serial processing. So that is serial processing of the code. Whereas once you give the input, all 4 operations can be performed simultaneously. Now, if there is a single processor, what will happen is, you imagine something like 20% of the code is like taking input, 20% for addition, 20% for subtraction, 20% for multiplication, and 20% for division. For example, yes, right? So if there is a single core, what will happen is all 100% task will be done by single processor. So there is absolutely no problem. What will happen if I add one more core there? First 20% actually does not affect at all. Reason is it is taking input and only one thread is working there. During this time, the second processor is idle. It is doing nothing. But once we give the input, maybe 2 operations can be carried out simultaneously, say something like addition and subtraction. Once these 2 are finished, then the 2 processor will perform multiplication and division. So in short, what will happen is first 20% is as it is. Okay, addition and subtraction previously on single processor need 20-20, but this time it will happen in 20, for example. And multiplication and division, like previously it is 20-20, maybe it is 20 years. So 20 plus 20 plus 20, like 60%. Remember, it needs whatever the time, 60% of the time. Reason is the serial processing part cannot be performed simultaneously even though you have a multiple processor. And this formula, Amdahl's law, this formula gives you about the speed up. Now, how it is calculated. Now you imagine 100% code, whatever my task is there, 100% is a serial. So when I say 100%, it is represented by 1, right? So 1 minus 1, 1 minus 1 here, it gives me 0. 0 divided by n gives me 0, and it is 1 divided by s, which is a serial processing. So which I mentioned is 1, 100%, right? So if it is 1, so 1 divided by 1 gives me 1. That means there is absolutely no speed up irrespective of value of n. You go on adding any number of processing core, doesn't matter. There is absolutely no speed up. So this speed up depends on how much of your code need to be performed, executed serially. Okay, so for example, here example mentioned is 25% is serial. So 25, now if you add those values here, definitely for 2 cores, the speed up will be 1.6, and for 4 cores, the speed up will be 2.28. And because this is 1.6 times and 2.28 times, you simply multiply by 100, so you'll get in percentage. So like speed up is 160%, something like that. Where meaning of 200% is double the speed, right? So that is the Amdahl's law. Next. Fine. So let us see the next part, the types of parallelism. For types of parallelism, it is broadly categorized like 2. One is data parallelism, and one is this one is data parallelism, and second one is task parallelism. Now this is very easy to understand. Just you need to remember the highlighted words, the same task and different task. Okay. So data parallelism means the same task will be performed on different subsets of same data. Subset of same data. Now this is important. Now when you see, for example, the example mentioned below here, suppose we want to sum the contents of array of size n. You imagine, like, for example, there are 100 elements randomly generated and stored in an array. Okay, and now we have a dual core system. That means two processors are there. Now one processor is running thread A, another processor is running thread B. So two threads are being executed on separate processors. Okay, so the same thing I mentioned, thread A running on core 0 and thread B running on core 1. Fine. Now, in order to perform this task fast, rather very quickly, what we do is, maybe first thread will sum the elements 0 to n by 2 minus 1. Because my index started with 0, it is n by 2 minus 1. Otherwise, I can say it is 1 to n by 2. Okay. So if 100 elements are there in C-like arrays, then first index is 0 and last index is 99. Okay. So the 50th element will be at the index 49. So the same thing, n by 2 minus 1, this will give me the, it is very simple words, half of the elements summation will be on thread A, that is on core 0, and rest of the elements, so from 50 to 99, element number 50 to 99, next half, that sum will be carried out by another core, another thread rather. So here if you observe, the task we are performing is just sum. What is changing? Thread 0 is doing sum, so it is sum, right? Whereas thread 1, it is also doing sum, right? The thing is, what is different? Data is different. But what is data here again? It is subset of same data. Like, for example, data is like we have 100 elements. Now subset of that is like first 50 elements and next 50 elements. This is called as a data parallelism. Whereas what is the task parallelism? Task parallelism, as the name suggests, different threads perform different tasks, and those different tasks may be either on same, here it may be on same data or maybe on different data. Important thing is tasks are different. Okay. Now again let me give example here. For example, I have 100 numbers, exactly same manner like previous example. Okay, and now I want to find out what is the average of all the 100, what is the minimum number from all 100, what is the maximum number from all 100. Now here I am considering same data, the 100 elements. The thing is, tasks are different. So previously we divided data, this time we are not dividing any data. Same data will be given to all three threads. One thread will compute its average value, maybe it will do some sort of summation divided by number of elements. Second thread will just kind of a searching where it will try to find out the minimum value out of 100, and third will try to find out the maximum value out of 100. So here the tasks are different, remember. Okay, so the same thing I mentioned here, like for example, two threads performing some sort of statistical operation like finding minimum, finding maximum, average, maybe mean, maybe whatever the different statistical operations are required. Okay. So on the array. So and maybe this array of element may be different data or it may be same data, doesn't matter. So these are called as types of parallelism, data parallelism and the task parallelism. Right. Next, the user level threads and the kernel level threads. Two types of threads, user level threads and kernel level threads. Now this is like an important thing where two types of threads are there. As mentioned, user level threads and kernel level threads. Now the difference between both is actually straightforward. User level threads are implemented by users. Who implements this is user. For example, whatever POSIX threads are there, Java threads are there, or threading concept implemented in Python, all these are user level threads. Okay. Whereas kernel threads are implemented by operating system, and for this actually hardware support is required. Okay. Anyway, we'll see the difference. How does it matter? Now, for example, if kernel itself is not multi-threaded, that means if kernel do not have implemented any threads, then if you are making use of threading applications, say for example, you have selected the Java programming language and you implemented one of the application with multi-threaded support, even though you have multiple cores in your operating system, threads are not able to utilize that hardware because, very simple thing, user level threads are not at all known, they are not recognized by the operating system, they don't know. Whereas kernel level threads, because they are implemented by OS, they are recognized by the operating system. Okay. Now implementation of user level thread is easy. You just need to go with simple API provided by a typical programming language. Whereas implementation of kernel thread is complicated because that has to be implemented making use of kernel data structures. So operating system will take care of that. So kernel has to provide it, right? Whereas here, anyway, maybe later we want to see different application programming interface provided by few programming languages. We'll select POSIX threads, then Python threads, even Java threads also. Okay, so that you will come to know how to create actually threads. Context switch time is less because that happens in user space. Here context switching time is more. So context switching is like switching from one thread to another thread. Okay, so that time is less in case of user level threads. Context switch requires no hardware support. Here hardware support is needed. Okay, so the difference between the user level threads and the kernel thread. If one user level thread perform blocking operation, then entire process will be blocked. This is actually a single point. If one user thread perform blocking operation, then entire process will be blocked. Meaning of this is very simple. For example, I have multi-thread application. Okay, multiple threads are there, and one of the thread is blocked maybe because of some reason. Then definitely entire process will be blocked. Whereas in case of kernel level thread, if one of the kernel thread perform blocking operation, then another thread can continue execution. Okay, so that is the case. That means if you need true multi-core programming, you must have multi-threaded kernel. And in the earlier slide, I already mentioned most of the modern operating systems have the multi-threaded kernels. I guess I mentioned the same point under the motivation. Now, because my kernel itself is multi-threaded, definitely I can write multi-threaded applications so that I can utilize the hardware. That is basic idea behind it. Okay. User level threads are designed as dependent thread. So that depends. Now that depends on what? That depends on underneath threads. Maybe like kernel level threads, where they are independent. Kernel level threads are independent. User level threads are dependent threads. Okay. For example, the Java threads are there, POSIX threads are there, and kernel level threads. Nowadays, most of the modern operating system kernel level threads, even Linux supports kernel level thread. Example mentioned I here is Windows and Solaris. So kernel level threads are there. So Windows also support. So Windows kernel itself is also the multi-threaded kernel, right? So that is difference between user level thread and kernel level thread. Now, this is one more topic regarding multi-threading models, and these multi-threading models mainly depends on how we can map the user level threads to kernel level threads. So this is important thing actually. This is regarding mapping of user level threads, whether I can say user threads to kernel threads. How we can map, and there are multiple options actually for this, and these options are, for example, first multi-threading model is many to one. So in my application, I have multiple threads, but my kernel itself is a single threaded. It is not multi-threaded. So if operating system is not able to utilize the hardware, there is no point to write application like multi-threaded. Okay. So many here, 1, 2, 3, 4 threads are there. 1, 2, 3, and 4. All these 4 threads are mapped to single thread at a kernel level. So many user level threads map to single or one kernel thread. Okay. Now, who does thread management? Because here is a single thread, all thread management has to be done by the library here in the user space. So this part is important. Thread management is done in user space. Now, anyways, though these are the 4 different threads, this is the single application. And if any one of the thread is blocked, maybe because of blocking system call, entire process will be blocked. Reason behind that is very simple. Whenever, say for example, this executes some sort of a blocking call, whenever this is mapped to the kernel, and if this kernel thread itself is mapped, the complete process will be blocked. Okay. So blocking of single thread makes entire process to be blocked. That is what happens with many to one multi-threading model. Okay. Next is 1-to-1. And what happens in case of 1-to-1 is, as the name suggests, for each and every user level thread, there is a kernel thread. That means my operating system itself needs to be multi-threaded operating system. So each user thread maps to the kernel thread. So 1, 2, 3, 4 user level threads are there, corresponding 4 kernel threads are there. And definitely this provides more concurrency. Now this kind of architecture, like my application itself is multi-threaded, my operating system kernel itself is multi-threaded, and I have multi-core processor. So try to understand. Application is not serial, kernel is multi-threaded, and multiple processors are also available. Then definitely it supports parallelism, and because of this parallelism, we'll definitely get more throughput. So it provides more concurrency. If one user level thread is blocked, only that will be blocked, rest will continue. Okay. So this allows another thread to run when a thread makes a blocking system call. Because only that kernel level thread is blocked, rest of the kernel level threads can continue. They truly utilize the hardware of multiprocessors. If multiple processors are there, they allows the parallelism. Okay. Only thing is now how many kernel level threads can be created, number of threads. And whenever user creates a thread, you need to create thread in the kernel. So that is actually overhead on operating system. Because I already mentioned the kernel level threads needs to be created by operating system, and they are not easy to create it. There is overhead involved. Okay. So this one is 1-to-1 multi-threading model. First multi-threading model we saw is many to one. This one is 1-to-1. Now next one is many to many. Now the like 1-to-1 we saw the drawback. For each and every user level thread we need to create kernel thread. So that drawback is tried to be removed here. So multiplexing is done. The mapping is not 1-to-1, but again it is not many to one. It is many to many. They will try to like make user level threads to a smaller or equal number of kernel threads. But anyways, multiplexing can happen. Maybe for example, this user level thread will be mapped here, second will be mapped here, and for third and fourth, for these two, 1 and 2, they will be mapped to the single one. So it is actually combination of both. Again, the advantage is, like for example, if this thread is blocked, rest of the thread can continue. If any one of these will be blocked, still these two can continue. So it is like taking advantage of both many to one and 1-to-1. Plus, we can restrict the number of threads in the kernel. No need to match number of kernel threads based on how many threads created by the user. So this one is called as many to many multi-threading model. Okay. Now the next one is like variations of many to many model. Maybe if the user needs a separate, maybe something like one important thread is there, parent thread is there for my application, and that I want to map to a separate kernel level thread. So that marking is allowed here with this 2-level multi-threading model. For example, there is one-to-one also, and there is many-to-many also. So for multiple threads at a user level, multiple threads. So it is like a hybrid for important thread, but then again, who will decide which thread is important, right? So like this variation of many-to-many model, it still multiplexes many user threads to a smaller or equal number of kernel threads, but it also allows a user level thread to bound to a kernel thread. This binding, one-to-one binding is also allowed it here. Okay, so this is multi-threading model. So if again I come back, this part is important, user level threads and kernel level threads, and then we need to map user level threads to kernel level threads, and for this mapping multiple models are there, like many to one. Many user threads are mapped to kernel thread, one to one for each and every user level thread there is a kernel thread, then many to many for number of user threads they will be mapped to smaller, definitely this is smaller or equal number of kernel threads. Okay, so this is many to many and sprite variation. Many to many is possible, but still it allows you to one of the user level thread to be bound to one of the kernel level thread. So this is two level threading. Any doubt till now? Any doubt till now? Because now we want to see the thread library, how to write multi-threaded application. Maybe we'll see example also. Before that, do you have any doubts regarding whatever we studied till now regarding multi-threading? So we started the definition of thread, what is thread, why it is lightweight, what are the advantages of using threads, okay, all that stuff. User level threads, kernel level threads, multi-core programming, that is important. Now coming to the practical oriented thing, the thread library. As I mentioned, we'll see thread library from three languages. One is POSIX threads, I just mentioned in front of you, and I am not going into depth of all the functions. The bare minimum functions I have selected here so that you will be able to write at least simple applications on that. Anyways, you can go on adding something, or you can go with manual pages. So POSIX threads. We'll start with POSIX. Before that, do you have any question? If there is a question, please put your question in Q&A section. Okay. Okay. There is no question, no problem. So let us continue. POSIX threads. I guess I already mentioned the importance of POSIX first of all. What do you mean by POSIX? Okay. So POSIX is nothing but even what is necessity of POSIX. See, whatever the concepts are there, not necessarily threads, but many of the concepts maybe like how to represent data, how to communicate, some sort of standard rules are required so that it is possible the applications will interoperate. Okay, it is possible to transfer the application from one platform to other platform, and for that what is needed is some sort of standard is required. So POSIX is like such IEEE standard, where the meaning of POSIX is portable P, that P stands for here, this P stands for portable operating system interface for X, where this X is initiated something like Linuxes, Unixes, but now X can refer to even Windows also. Okay, so portable operating system interface for X, so that it is possible to write portable application. One application developed on one platform should execute on another platform if you just modify the what I can say, the operating system. Okay, now in that term we say like Java is platform independent, C++, because the origins of C and C++ is to write portable applications, and because you can port, that means again they are independent of platform. So in order to write platform independent applications, otherwise everybody has started developing their own concepts like thread. Everybody has implemented their own threads. Okay, so let us start the POSIX threads. Yes, you can call it from C and C++ language. So POSIX threads are supported by both C++ compilers. The thing is, again, in order to compile the programs with POSIX threads, maybe you need to make use of LP thread. Let me. For example, suppose I am making use of CLang or GCC-LP thread. Okay, and suppose name of my program is prog.c, something like this. Now this part is required. Now few operating system by default make use of this LP thread, and few or not. It is better if it is not working properly, or if maybe it is giving some sort of a linker error for any thread related function like pthread_create, then you must compile such application with this option LP thread, GCC-LP thread. Now this is the header file, pthread.h. This is the header file which supports all the functions. Now only important function here is, I can say, pthread create. Rest of the functions are very simple. Okay. Now this pthread.h, it provides you one new data type called as pthread_p. So this is just like each and every process has got unique process ID on exactly same lines. For each and every thread there is a thread ID called as a thread handle also. So thread ID or TID, in short I can say TID. Okay, so you need to declare a variable. Anyways, we are going to see one small program on this. You need to declare one variable, something like what I can say. I'll declare one variable pthread_t, for example TID, and then because star is there, that means I need to pass the address of that. So when thread is created, pthread_create will assign some thread ID to it, and you consider this as a thread handle. Next thing is const pthread_attr_t. This is one of the structure that represents different thread attributes. To make our program simple, because this is a pointer, we will simply keep it as 0. Now what are the thread attributes? There are so many attributes for thread, like whether it is a detached thread, whether it is daemon thread, or it is joinable thread. Okay, I don't find this correct time to talk more on attributes here. Otherwise, then things will become complicated. To make it simple, let us put it as a 0. That means whatever the default thread attributes are there, maybe something like nice value. Nice value is like in case of a Linux operating system, a nice value actually represents the priority of the thread. Okay, so that even nice is the command itself. NICE, nice is the command. You try nice command on Linux platform. So this 0 will keep it as it is. Now important part is again here about this one. Anybody understand this? Void star in parenthesis star, then start routine, then void star and comma. Remember, this is pointer to a function. This is pointer to a function. So this is also called as a callable. Callable. So this entity is callable. Function is callable. We call the function, no. So that means you need to write a function. Now try to understand the difference between process and thread now. In process, we simply make use of fork, and fork creates a duplicate copy of if this is a process, if you do fork, 2 copies of the same process will be created. Right? So if I call this as a parent, yes, this is parent as it is. Now don't think like fork creates 2 different separate processes. No, it creates only one. Just I am showing this parent here, and this is not child process. And in order to replace the memory copy, now whatever parent's duplicate thing is there, I just want to change it, and that can be done with exec that we have already studied. Right? This can be done with exec. So first of all, we need to create a child process, then we need to call the exec, and exec will load something from hard disk, which is the program, and then it becomes a process, and that becomes child process of whatever your original parent process. So this complication is not required in case of threads. You just need to write a separate function and pass the function to this one as a third parameter to pthread underscore create. And even while passing it is in single times, it is a pointer to a function. That's it. And pointer to a function is just name of the function. For example, suppose I have a function called as say my function. If this is my, then pointer to this function is nothing but just my function. Now note that here I am not giving any opening and closing parentheses. There is no opening and closing parentheses. If there is opening and closing parentheses, then we'll call this as making call to a function. It is like calling a function, right? Whereas this is the pointer. So this is a pointer. Whereas this first one, this is actually calling a function. So that is the difference. Okay. You're getting it, no? Now, what kind of function is required here? What is meaning of this void star? Remember, we need to pass a function such that that function's return type must be void star. This is return type. Void star is a return type. Here you just give name of the function without any parenthesis, and this void star is parameters. So this part is important. These are the parameters. Okay, and this one. This one, void star. Remember, this is the return type. So we need to write a function whose return type is void star and which will take only one parameter of type void star. And you simply pass that function here. Last thing is you need to pass void pointer, which is the actual argument. So whatever this void star is there, the same argument you need to pass. Of course, if you don't want to pass any argument, you simply say 0. If you want to pass the argument to the function, you need to convert it to void star. The question is, what if I want to pass multiple arguments, not single argument? Now there is no straightforward way for that. Whenever you want to pass multiple arguments to the multi-threaded thing, the pthread underscore create function, then you need to write a separate structure with whatever number of arguments you expect and make use of pointer of that structure, convert it to void star. So through pointers you can manage it. That is pthread underscore. Anyway, we are going to see example on this. Like process can be exited with exit call, thread can be terminated making use of pthread underscore exit. And you can mention whatever the return value is there. Same like your exit call for process. Okay. And this third one is pthread underscore join. Exactly same thing we studied related to process, that is wait or wait PID. Where parent thread or maybe any other thread will wait for completion of this thread. Now I am saying completion of this thread. So when I say this thread, that thread is represented by the first parameter. And this is exactly same which is created by pthread underscore create. So this is the linkage. So something like what we do in file handling. We say fp is equal to f open, and with f open, what happens is we are getting the file pointer. Once we get the file pointer, then that file pointer can be utilized for further calls like reading and writing and something like that. Same thing, pthread creates gives me thread handle or say thread ID, and that can be utilized here. So pthread underscore join means wait for completion of this thread, and whatever the return value given by that thread will be taken here. That is the second argument to process thread. Okay. Any doubts in this? Any doubt? Is there any doubt on POSIX threads? I mentioned about how to compile programs. If you have any doubt, please ask. Now just 1 or 2 minutes is, yes, 1 or 2 minutes are remaining. So before going to next, now this is Python threads. Now threads in Python is very simple comparatively than your POSIX threads. The package required, like I mentioned in case of C language, you need to import pthread.h. Now Python module threading is required. So for the Python language, what we need is the threading model. So this one is the module you need to import. This is how to create a thread. So threading dot thread. So there is a class called as a thread. So one thread class is there, and this class has a constructor. You can call constructor like this, where meaning group. Yes, you cannot use group, by default value is 0. So right now this is not implemented. Target is name of the function, it's a callable. Same thing what we do in POSIX thread. It is name of a function which will be automatically invoked by something called as a run method of this class. Name, yes, name, you can provide name to the thread. Again, all these things are optional. So default name is like thread 1, thread 2, thread 3. So unique name will be automatically created. So that is the name. Then arguments. Now for arguments, if you are already aware, this is called as a tuple because that is in between the opening and closing parenthesis. So this is a tuple. So there are two ways of passing argument, either with this one tuple or with keyword arguments. Keyword arguments like name and value arguments kind of thing is there. So this is a dictionary. Keyword arguments are implemented using dictionary, and normal arguments are implemented with tuple. Okay, so that is how to create a thread. Then you need to start the thread. It starts execution of thread. Whereas in case of POSIX thread, whenever you create thread execution will automatically start. Next one is T1.join. Same thing. The join method is used where another thread waits for completion of this thread. Okay. So threading.thread, it creates a thread with whatever the parameters passed, and it is returned back. And then this return value will be used to start it, and maybe another thread will execute something like T1.join. So programs we'll see in tomorrow's session. So right now we'll stop here. Thank you.